Good morning, David.
Good morning.
You mean?
Yep. Hi, Claudio.
Good morning. Sorry to wake you up so early today, but
Well, you did me a favor by not getting me up at 5 o'clock in the morning.
we move out. Actually, we postpone. No, it's hard. It's also hard when we are having people coming from Japan or that region.
I understand. So I appreciate all my colleagues.
Sort of a mixed balance. So how things are going there? Good.
Very well. Yeah. Yeah. Things have been busy. We're having a little bit more of a surge of COVID and influenza.
The flu, yes, we have.
And then the kids have gotten RSV. So our pediatric hospitals are completely filled with kids with RSV. So they're not as sick as we see with some of the other infectious illnesses in kids, but they are still occupying hospital beds. So it's been very busy. Yeah,
I can imagine. No, it's a very hard time. I mean, you don't understand where the COVID finish, when the flu starts, where the other bugs are coming in. It's really hard, and everything is actually hampered by making plans, because you really don't know if you can deal with this situation if you are sick.
Yeah, now that we all are vaccinated and boosted and so forth, we don't get so sick, but it's still, there are a lot of inconveniences with travel and things like that,
in spite of the fact that we have people got the fifth shot of the vaccine, they still have some symptoms, particularly the weak person. So it's really hard. And then if you have to travel, you have to make special arrangements and blah, blah, blah. It's really inconvenient. Okay. At any rate, so I'm very glad that you can be the last speaker of this year, the last Yellow Seminar. Yeah. And I think that it's almost, it's time. It's 7 o'clock in your,
we're ready to go. Yeah.
You're ready to go. Okay. So thank you very much. I mean, let's start the last Yellow webinars of the year. And as the Romans say, dulcis in fundo, which is ice on the cake. We're really ice on the cake today, because we have the pleasure of having Stevenson with us. David is a professor of medicine and pediatrics at Stanford University. And in addition, David is a world-known expert in bilirubin metabolism, and he provided excellent and totally new information on the production and modulation of bilirubin. So David, please, podium is yours, the virtual podium is yours, and thank you very much for accepting our invitation.
Thank you, Claudio. And again, thank you to all of you who agreed to shift the time a little bit. So I didn't have to get up at 4 in the morning to be ready to talk to you at 5 in the morning on the Pacific Coast, but I appreciate that. So it's a much more reasonable hour for a neonatologist. More recently, most of my work has been focused on the discoveries that would be important for understanding the causes of preterm birth and preeclampsia and prevention of those two conditions. But we still do a lot of work on the biology of bilirubin, and in particular bilirubin production and its inhibition. And that's what I'm going to talk to you about this morning. I appreciate the opportunity. I have nothing to disclose. So let me begin in the usual way that I do by describing neonatal jaundice by analogy to a sink. The turned on spigot represents the processes of bilirubin production, and the drain represents the processes of bilirubin elimination. It's easy then to understand that if the rate of production exceeds the rate of bilirubin elimination, then the level in the sink begins to rise. And in this analogy, the sink represents the circulation. Of course, the capacity of the sink is limited mainly by binding to albumin. So there's a finite capacity for this sink, although obviously abnormalities of bilirubin binding as it relates to binding to albumin can cause leakage of the sink, and then a premature movement of bilirubin outside the circulation into the tissues. This is particularly likely to take place in the context of increased bilirubin production, where the binding capacity is more rapidly exceeded. And people can anticipate this in the clinical context of a very rapid rise in the serum bilirubin or plasma bilirubin level. Now, the turned on spigot is the two-step catabolic process for heme catabolism. And the first step in this reaction is a very ancient step for many life forms on this planet, including prokaryotes like blue-green algae, like plants, and of course animals like us. And it has many different roles in biology, and I'll come back to that a little bit later in this talk. But the first step is an elegant reaction in and of itself, requiring NADPH donated from the cytochrome P450 system in animals, and oxygen. And in that step, the protoporphyrin 9 ring is cleaved, carbon monoxide is eliminated, ferrous iron is also eliminated, and biliverdin is produced. In mammals, very rapidly in the cytosol, biliverdin is further changed, again with the requirement for NADPH and another enzyme, biliverdin reductase, to bilirubin. So it's important to note, and it's convenient for investigative purposes, that bilirubin and carbon monoxide are made in equimolar amounts. Now, this reaction is nearly ubiquitous. It's in every nucleated cell in mammals. People often, if they're not familiar with bilirubin biology, think that it might be only happening in the liver or something like that, but it's actually happening in every cell. And it's an incredibly important reaction that goes beyond simply producing bilirubin. And again, I'll come back to that a little bit later in this talk. Just as a quick side, biliverdin is an important precursor of phytochrome in plants. And people forget that heme synthesis is critical to plant life on this planet as well, and also defense against oxidant stress. Just like this enzymatic system is important in antioxidant antioxidation type reactions in our bodies. But in plants, this first step is absolutely critical, and it's important for production of this other chromophore, which is incredibly impactful in plants, because when light shines on it, it will also transform itself. It's very similar to bilirubin in many ways, so it interacts with light. It'll move into the nucleus of the plant cell and is involved with regulating gene expression, involved with all different kinds of essential plant processes. Ultimately, also guiding chlorophyll production, which is the way plants, in fact, generate or convert light energy into other forms of energy that can be used in plant life. So I think this reaction is very important one in nature. It's very old, and it's something that it's important to understand, particularly in the context in which we consider it as pediatricians related to bilirubin production. So this is the turned on spigot, that this two-step catabolic process in mammals, which leads to the equimolar production of bilirubin and carbon monoxide. Now, when the level in the sink exceeds the capacity of the sink, or put it in the terms of bilirubin biochemistry, when bilirubin binding is exceeded or bilirubin binding is abnormal, then the bilirubin will leave the circulation, again with other factors modifying that, like acidosis when you're dealing with the ZZ isomer. But this can lead to the syndrome with which we're all familiar, which is referred to as acute bilirubin encephalopathy. And this is the toxicity seen in the first weeks after birth. The early phase is characterized by lethargy, hypotonia, and poor suck. The intermediate phase is characterized by irritability, hypertonia, high-pitched cry, fever, and poor feeding. And the advanced phase with retrocollis, epistatonus, high-pitched cry, fever, apnea, coma, sometimes seizures, and death. One of the things which is very misleading is, of course, if a child survives this phase of biliary encephalopathy, not much appears clinically for a while on physical examination, but later we see chronic bilirubin encephalopathy in some of these children. This is the permanent sequelae of bilirubin toxicity. It's characterized by a very disabling form of cerebral palsy, which is athetoid in nature, auditory dysfunction, gaze dysfunction, enamel dysplasia when the permanent teeth erupt, and sometimes intellectual and other handicaps. Although what makes this such a devastating condition is that oftentimes the children are intellectually basically spared, and yet they're trapped inside of a body that is not able to function. So it's a horrible disability when it occurs, and it's something that we would like to avoid. Now, the way we've dealt with this historically is with phototherapy. And of course, phototherapy works, again, because bilirubin interacts with light in unique ways, particularly at a wavelength around 478 nanometers, although most of our blue phototherapy banks are around 450, but they work well enough. And it causes, when we apply these lights to individuals that have bilirubin in their circulation and also in their tissues, to cause structural isomerization and produce lumirubin, but also very rapidly configurational isomerization, producing water-soluble easy isomers, which immediately are more water-soluble and can be excreted in bile without conjugation. And Tor Hansen and his colleagues showed how rapidly this can occur with some 10-15% of bilirubin being in this form after the application of light, even before the diazo method begins to reflect the degradation of bilirubin and its exit from the circulation. Photooxidation also occurs, but it's not a major pathway. One of the things I've always worried about, and this is a big part of this story, is that sometimes physicians participate in what's called ambitious overgeneralization. This is something Bill Silverman warned Phil Sunshine and me about. And of course, he was writing notes to many of us in the field, but this is one of the ones he sent to us, reminding us that this was something that was unfortunately commonly practiced and could lead to disaster. And in the case of phototherapy, this, in fact, probably is something that has happened. And that is that after studies in the 1970s, the National Collaborative in the US, where it was demonstrated that phototherapy could decrease the need for exchange transfusion, and it appeared to be safe, although the study was not designed to demonstrate that, and certainly not in very small babies. We concluded that this was a very safe therapy, and I think it probably is for most full-term or near-term babies, but it was never tested really in randomized controlled trials in smaller babies, which in fact were increasingly the patients that we were taking care of, babies much smaller than those that were ever enrolled in the study in the 1970s. And of course, these babies were much more translucent. And I knew this because I was also doing work at the time using visible light to basically identify structures and function in living animals as well as in humans. So I knew that light could penetrate the tissues. And in fact, in the most immature infants, you can see structures, even with the naked eye. We were using computers to do this in situations where you couldn't see really beyond the layer of the skin. But with computers and taking advantage of the absorption of light and light scattering, you could actually generate images of internal structures. So light definitely was penetrating the tissues of these smaller, more immature children with less stratum corneum and thinner skin generally. So we asked the question, is it possible that visible light has an adverse effect in small premature infants? And I convinced my colleagues at the NIH that this would be important to study. And so Bill O and I and others designed a trial, which ultimately was completed and then described in the New England Journal, called Aggressive versus Conservative Phototherapy for Infants with Extremely Low Birth Weight. And we designed it in a way that we could begin to understand whether phototherapy would have any effect beyond protecting kids from bilirubin, which we believed was certainly necessary in these kids. And it turned out that it was, but whether it had some other effects that were less desirable. So the primary outcome of this study was that aggressive phototherapy did not significantly reduce the rate of death or neurodevelopmental impairment. So in that sense, it was a negative study for this combined outcome. But we had planned two secondaries, which were really important for understanding what was going on in these tiny babies now exposed to very aggressive phototherapy or less aggressive phototherapy. What we found in the two secondary outcomes were offsetting effects. The rate of neurodevelopmental impairment alone was significantly reduced with aggressive phototherapy, reflecting our belief and the general understanding that phototherapy was important for protecting kids against even high single-digit levels of bilirubin in the circulation, which could lead to neurotoxicity. But also, ironically, this reduction was offset by an increase in mortality among infants weighing 501 to 750 grams at birth. In other words, the smallest, most immature, and most translucent infants. So these two offsetting effects of light led to the overall trial resulting in no difference whether we used either aggressive phototherapy or a more conservative approach. So returning to the analogy of the sink, we then had to think about how we would proceed. Should we not be able to take advantage of phototherapy in the way that we had historically for term infants and more mature preterm infants with thicker skin, basically. And so the logical target then was going to be heme oxygenase, the first step in this two-step catabolic process for heme. But if we were going to do that, understanding that this was a nearly ubiquitous reaction, not just happening in the liver, but happening in every nucleated cell throughout the body and many different tissues, and that there are different isozymes of heme oxygenase. The constitutive form may be important in some of these other biological processes. We thought that it would be important to consider the heme oxygenase target in a context. And of course, this context is complex. Now, as pediatricians, we always thought of the heme oxygenase system in terms of its toxic effects, because it produced bilirubin, caused jaundice in newborn infants in the transitional period after birth when conjugation was limited, even in normal infants. And of course, we know there are polymorphisms that can alter that and make it even more likely for kids to develop jaundice. And this could sometimes cause neurologic disturbances, which could be transient, but in some kids, under some conditions, particularly if we had concurrent infection or something of that sort, you could develop permanent injury called kernicterus. Even carbon monoxide, we would tend to think of as a diatomic gas that could bind to hemoglobin, displace oxygen, interfere with oxygen delivery to tissues, and even bind to the cytochrome system, causing mitochondrial dysfunction and death. And we were encountering that, of course, in environmental exposures primarily. And of course, iron, ferrous iron in particular, through the Fenton reaction, could generate hydroxyl anion and is very reactive and can cause tissue injury and again, cell death. So we were looking at basically the dark side of this heme oxygenase system. But in fact, and most people, I know Claudia has been very interested in this more recently, and certainly Tony McDonough was interested in this as well. There are many potential beneficial effects of this enzymatic system. The biliverdin bilirubin shunt in all cells has important antioxidant, anti-inflammatory, and anti-apoptotic properties. It basically helps to maintain the redox state of the cell and may be important for gene expression. Carbon monoxide, that diatomic gas, which we thought of as a poison, is an important signaling molecule and can cause vessel relaxation through calcium-dependent and potassium channels, and can also act through soluble guanylyl cyclase and cyclic GMP to cause vessel relaxation. And in addition to antiplatelet, anti-apoptotic, particularly in endothelial cells, and anti-proliferative properties in vascular smooth muscle cells, and it may even be involved in neurotransmission. Acting through the p38-MAPK pathway, it can contribute to the inhibition of pro-inflammatory cytokines. And acting through VEGF may be important in angiogenesis, and has led us to become interested in placental vascular development and its relevance to preeclampsia. Again, ferrous iron, if it's bound to ferritin, can actually also contribute to antioxidant, anti-inflammatory, and apoptotic situations. Well, if we were going to take advantage of that molecular relationship that I told you to study bilirubin production, we had to understand the endogenous sources of carbon monoxide, let alone the exogenous sources where you would have to correct for ambient contamination. Fortunately for us, heme degradation is the major source of carbon monoxide, mainly from senescing red cells. That's about 70% of the total, but also ineffective erythropoiesis and many other hemoproteins. And there are many other hemoproteins, catalases, peroxidases, even endothelial nitric oxide synthase. So there are a lot of other heme-containing molecules that ultimately, when they degrade, can take advantage of this system. Now, just to put the perspective of scale here, for those of us interested in bilirubin, if you look at the number of molecules of hemoglobin in a single red cell, it's about 270 million. And of course, there are four hemes for each of those hemoglobin molecules. And then there are, which really gives you a sense of scale, about 25 trillion red cells in an adult. So there's a hell of a lot of heme that's going to be degraded, even when it's happening at a normal senescence rate. And that's just with red cells and not these other heme sources that I just mentioned. So you can imagine what happens when we have a hemolytic condition, which puts kids at extreme risk for producing a lot of this pigment too fast and exceeding their capacity to bind it and keep it in circulation. There are non-heme sources. We were the first to describe lipid peroxidation as a source of carbon monoxide, and also photooxidation. We demonstrated that in animal systems and in vitro. And this can be useful, but fortunately, in most instances, although it sometimes is probably contributing, at least in part, to the total CO production, which reflects the total bilirubin production, most of the time it's not a factor. And so we can depend on carbon monoxide excretion in the breath of infants or carboxyhemoglobin in the circulation as reflecting mainly heme degradation. So I spent most of my career making measurements of the excretion rate of carbon monoxide in different species, rats and mice and monkeys in particular. Working with the baby monkeys was quite easy. They're not too different than human babies when they're very immature, but they mature very quickly. And once you have a mature monkey, you've got your hands full. So we work very closely with our veterinary colleagues to do this work. But it gave us some insights, as I'll show you, as we began to work on ways to control bilirubin production. Of course, we demonstrated in a rat model that what I have been telling you is in fact true. If you inject damaged red blood cells, sort of mimicking the hemolytic circumstance, you could collect carbon monoxide in the animals in a time frame that reflect splenic sequestration of the damaged red blood cells and their destruction, and then ultimately production of carbon monoxide through heme catabolism in a time frame that was roughly 8 to 12 hours. And you collect all of the heme that you injected as carbon monoxide, again reflecting that one-to-one correspondence between heme degradation and CO production, which of course reflects bilirubin production. So this, in fact, was confirming that one of the most sensitive ways of studying hemolysis in animal systems, and certainly also in humans, is the measurement of carbon monoxide. What we could do in animals, we also did in humans. We built this chamber and we're able to study hundreds of babies under a variety of conditions. We could not study the kids on ventilators using this approach until we developed more sensitive ways to deal with the high gas flows. But in this system, we were able to study many infants with a variety of conditions. And same as what we saw in the animal systems, we began to characterize what was happening in human neonates even before they would become clinically jaundiced. And as you can see from this graphic, this is a cartoon of real data, though, that shows the excretion rates of different conditions. The term infant, of course, produces 2 to 3 times as much bilirubin on a body weight basis compared to an adult, mainly because of the shorter red blood lifespan and the slightly larger red cell mass on a body weight basis. Preterm infants, for those same reasons, produce even a little bit more than term infants. In these data, I did not include the extremely preterm infants, where their red cell mass begins to be consequential in terms of total bilirubin production relative to their shorter red cell lifespan, so they don't have quite the increase compared to some of the larger preterm infants. But you can see the effects of a hematoma or polycythemia. You can see infants of diabetic mothers, abbreviated IDM, who have increased production rates, sometimes from basically polycythemia, but other times from ineffective erythropoiesis. So even the babies that are not polycythemic can have increased production, contributing to the increased propensity for jaundice in infants of diabetics. And then you can see the effects of ABO incompatibilities or heterospecificity and RH disease, where there's even more severe hemolysis. And so it's easy to identify infants even before they become very jaundiced in the immediate period after birth, using CO estimates of CO production either in the breath of the babies or as carboxyhemoglobin in their blood, corrected for ambient carbon monoxide, of course. Over the years, we actually contributed to a lot of different end-tidal carbon monoxide devices. The little c, ETCO-C, stands for the correction for ambient. The ETCO Analyzer 1 was the prototype we built in the lab. Hank Vreeman did this, and we built a whole bunch of them for the studies that we did in the network, where we worked at scale to see the what general populations look like in the term and late preterm population. And then there were several generations of the commercially available CO detection devices. I don't have interest in any of these companies, so I'm not making a pitch in that regard. I think the CoSense is still available and is used by some institutions in the US, but mainly now in China. And it's a very easy device that can estimate carbon monoxide production by measuring end-tidal carbon monoxide in the breath of very rapidly breathing babies. Now, this is something I mentioned, I think I mentioned earlier, but it's important to understand that infants with hemolysis and hyperbilirubinemia are at higher risk for neurologic injury. Tom Newman, colleague at UCSF, whom I've worked for years off and on, used to say that, it doesn't really make any difference. It just was the level of bilirubin circulation and whether you can bind it that would make the difference. And a lot of babies could tolerate bilirubin levels in circulation of 25 to 30 milligrams per deciliter. But even he changed his mind when he reanalyzed the large collaborative perinatal project and found out that kids with hemolysis actually were at higher risk, even given a similar bilirubin level to individuals within that population who did not have hemolysis. And this is an important concept, and it fits with what I told you at the beginning of this talk, which is that if you're producing bilirubin at a very high rate, there's only a certain amount that you can keep in circulation, which would be the amount that you measure. So even if you produce more and more over time, the level in circulation is not going to change that rate. It may bind somewhat to red cell membranes and a few other places, but it's not going to really change what it can be in circulation, it's all going to move outside the tissue. And so individuals that have increased bilirubin production, for example, caused by hemolysis over any length of time, are very likely to have large tissue loads in addition to whatever their serum or plasma bilirubin level might be. And a perfect example of this is if you take a child that gets to a level of, let's say, 25, and they are a breastfeeding infant, and it takes them a week to get to that level of bilirubin in the circulation is quite different than a level of bilirubin that a baby got to in about, let's say, 12 hours because they've been hemolyzing. And so those two babies are not equivalent given their two bilirubin levels. You have to consider the dynamic of the process, which means if they have high production because they got that rapid rise because of hemolysis, for example, they'd be much greater risk for neurologic injury. So it's not just the bilirubin level that you see when you make that measurement, it's what's in tissues, and bilirubin production is a large determinant of that, particularly when you take into consideration the element of time. So here's the target. And of course, I've now raised questions about whether it is a straightforward thing to simply hit the target, control the production of bilirubin, which would be great for us worried about jaundice. And we could measure that effect of a drug like that by just measuring the carbon monoxide production rates, either through breath, CO, or again, as carboxyhemoglobin in the circulation. But there was a lot to worry about. As we began to look at these compounds, which I began to do in the 1980s, along with many others, in particular the group at Rockefeller. And we looked at just about every single analog of heme, some of them having different metals in this protoporphyrin 9 molecule. And but the ones that turned out to be the most interesting were initially tin protoporphyrin, which turned out to be too toxic. And then tin mesoporphyrin, which was used in many human trials, but it's still not approved by the FDA because of its potential side effects, mainly photoreactive in nature. But because of its potency, you could use it at a lower rate, and I think you could use it safely under some circumstances. But the FDA has never approved that, partly because of these kinds of concerns about photoreactivity. But there were others that seemed promising, and they had naturally occurring metals in the protoporphyrin ring. One of these, zinc protoporphyrin, is a naturally occurring protoporphyrin. In other words, nature had made a choice of the different heme analogs, and this particular heme analog is already involved in the regulation of how the body deals with heme. And you have to remember that heme is a pro-oxidant, and keeping it bound in circulation to albumin or to hemopexin, and also catabolizing it, is very important for maintaining our balance of oxidation and antioxidation. I know this is a topic, again, that Claudia is very expert in now, and I think he's written a very nice review of this in terms of how we have to think about this system in this regard. But zinc protoporphyrin is a molecule that, in fact, helps to regulate the system, and then it's already increased slightly under certain conditions that we encounter clinically and also in preterm infants. So in the work that we were doing, before we rushed to use one of these heme analogs, even zinc protoporphyrin, as a potential therapeutic, we considered criteria for potential anti-hyperbilirubinemia drugs to include the following: a biocompatible central metal, that would leave tin out, a potent HO inhibition, or at least sufficient for controlling the production of the pigment, negligible degradation, just in case the metal in the ring was not biocompatible, negligible inhibition of other enzymes, which zinc protoporphyrin does not have a property like that, whereas tin mesoporphyrin does affect certain other enzymatic systems. Negligible photoreactivity. The zinc protoporphyrin is a non-photoreactive, naturally occurring protoporphyrin. An optimal duration of action, which would be short. And this, by the way, was another problem with tin mesoporphyrin, because it had a very long duration of action and tissue time. And the FDA has never really been comfortable with that either. And then negligible hemoxygenase 1, the inducible form of the enzyme upregulation. In other words, if you gave an analog that can inhibit this reaction, but you induced more production of the hemoxygenase, you would actually be shooting yourself in the foot, so to speak, by increasing the system's activity, and you'd have a shorter duration of action than you wanted, or perhaps other complications because of the other effects that this system has in other tissues. So negligible HO1 upregulation would be important. And of course, as I'll show you, the tin compound did have upregulation as a persistent feature. So to study that, we created a tool, which is in vivo bioluminescence imaging. And we were the first to take advantage of the fact that, just like a firefly, if I knew that light was getting into tissues, I also knew that light could get out of tissues. We don't do this in humans, but we can do it in animals to study how the hemox system would respond to inhibition using these heme analogs. This is a competitive inhibition. So we created the transgene for this purpose, so we could basically look at the upregulation of heme oxygenase, preserving the promoter, and created this transgene, the HO1 luciferase transgene, that we could use in cells and tissues and also in animals for the study of how these inhibitors would affect the upregulation of this system, because we knew that it had these other effects in other tissues. And we did this because we knew this system was a tightly regulated system because of its important role in oxidation and antioxidation, and also if you're interested in bilirubin production. So it had tight regulation due to the toxicity of the different products of this reaction: carbon monoxide, ferrous iron, and bilirubin. There was tissue-specific expression of this. The amount of inducible form varied from one tissue to another, and so relatively speaking, the constitutive form as well. There was developmental regulation. It was a key molecular target, as I've just described, for therapy. And the ex vivo assays were slow and provided only a snapshot, and I could look at things in real time using this system in animals. So the HO1 Luc fusion looked like this, and we can now study all the activating stimuli of the heme oxygenase enzyme. And you can see from the different factors that affect the induction of HO1 expression how important it is in not only antioxidation but oxidation. It sits as a fulcrum for maintaining a balance, which is important for many living forms on this planet, which is rich in light, oxygen, and iron. So the transgenic animals, of course, we could see homozygosity just by putting them in the cameras, and now we had ways of studying animals under various kinds of conditions, and also when we treated them with these heme analogs. And we just picked the animals that were appropriately expressing the luciferase in response to the luciferin that we administered to them, which is a non-toxic compound. And then we could study their heme oxygenase regulation quite easily. And we did this for all of the different analogs that we were interested in. And I'm just showing you zinc protoporphyrin, tin mesoporphyrin, and zinc bisglycol. Zinc bisglycol was just as potent as tin mesoporphyrin. It had a biocompatible metal and other desirable properties, but it was also photoreactive, and so we did not use it. But you can see it didn't upregulate the system at all. Tin mesoporphyrin upregulated the heme oxygenase system in response to the inhibition, and zinc protoporphyrin only did it briefly, which was again reflecting probably the nature's choice of an analog that would not perturb the heme oxygenase system through gene upregulation when you administered it, or if it increased in concentration naturally in tissues under some of the conditions that we encountered. So we studied this molecule in rats and mice, and then ultimately in monkeys. And monkeys have a bilirubin hyperbilirubinemia pattern, which is quite similar to humans, and you can see that here. They have a lower level, and it's a shorter interval of time for it to peak, but it has a second phase, just like mammals, other mammals do, like people. So it was a good model for studying neonatal hyperbilirubinemia. And this is exacerbated in premature monkeys, who are a little bit harder to work with. But we showed that zinc protoporphyrin, cutting right to the chase, could treat these animals if we gave them, again, damaged red blood cells, just like we gave to the rats when we were establishing the validity of this system. And you can see that when we gave them damaged red blood cells, they produced bilirubin as reflected in the estimate of total carbon monoxide production, which is reflected here in as carboxyhemoglobin, and it's in the red bar. You can see, compared to the saline solvent, that they did have increased bilirubin production. You could inhibit bilirubin production quite nicely, and that was easily observed using the carboxyhemoglobin levels if you gave tin protoporphyrin only 40 micrograms per kilogram. And it goes right back down to the normal production rates. And the beauty of this is that you didn't have to suppress bilirubin production completely or interfere with hemoxygenase in many other tissues. You could simply do it for a short period of time and only as much as you needed to control for hemolysis. And of course, more important than inhibiting the production of pigment is to control the bilirubin levels. And this just shows you that although conjugation still has some influence over what your circulating levels are going to be, that by controlling bilirubin production, you can control circulating bilirubin levels quite nicely in this hemolytic jaundice model in rhesus monkeys, which we felt was pretty convincing with respect to how a compound like this could be used in human neonates. And there were no safety issues in the rhesus monkeys that we identified in this early work. So again, moving very quickly towards where we are right now, we knew that zinc protoporphyrin, after all these years, having tried just about every other compound, the one that nature picked was better, but it wasn't easy compound to work with in the laboratory, and it was not orally absorbable to any great extent. And so we wanted to work on a formulation that would make it easily administered intravenously, but also orally. And we created a compound, zinc protoporphyrin lipid, with 10% zinc protoporphyrin. And then we used two already approved, FDA-approved endogenous phospholipids, DPPC and DSPC. And we use them as the main constituent of this synthetic drug, lung surfactant, which had already been approved, and used that same surfactant lipid profile to create the zinc protoporphyrin material for treatment. And we then did in vitro testing of potency using a protocol like this. I'm not going to show you these data, but we took advantage of some of the systems we developed for looking at hemoxygenase inhibitory potency in cells, and then we looked at phototoxicity as well as chemical toxicity, and we use a system like this. And we did this work also in vivo, and this here shows you the system we use for looking at this in vivo, because we wanted to make sure that, unlike tin mesoporphyrin or even zinc bisglycol, that there were not phototoxic effects or chemical effects that would make this not a desirable heme analog for inhibiting total bilirubin production in a human neonate. And what we found is that the zinc lipid formulation is an effective inhibitor of liver HO activity in vitro and after gastric administration in these mice. We've not done this work in animals, in monkeys yet, but it appears to be safe, and we've seen no toxic effects in the animals that we have studied. And most importantly, it had no photo or chemical toxicity, unlike the tin mesoporphyrin analog. And so we think it shows promise for human use. This sets the stage for a different approach to neonatal jaundice, where we can look at production rates and elimination rates and categorize infants according to whether they have low or high production or fast or slow elimination, with the individuals who would be at highest risk being those individuals who had slow elimination in the context of high production. This is something you can see clinically. Now, you can get some sense of elimination simply by watching the rise of bilirubin in circulation. But we also know enough now about polymorphisms. And with the current tools, it becomes easier to identify individuals that might be at risk based on their polymorphisms to get an estimate of who might be a slow eliminator. And of course, we also know that there are differences in heme oxygenase production capacity. And we get some idea of that as well by looking at the mutations in the gene that relate to whether you can produce the pigment at a very high rate in response to a stressor or not. And also after birth, you can monitor these things as well if in fact your before birth estimates are not as accurate as they need to be. With that information and a heme analog of the sort that I described, like zinc protoporphyrin, a naturally occurring protoporphyrin with a biocompatible metal in the ring, and can easily metabolized after a short duration of action, you can then think about the nomograms that people are using clinically. Of course, these are being modified in the next generation of AAP recommendations, but you can understand how increased production would and slow elimination, if you look at the way this graphic is set up, would drive you above the thresholds where you would apply your various therapies. But if you understand what controlling bilirubin production can do with respect to limiting the production of the pigment in the context of hemolysis and keeping the levels lower, then these individuals, the ones that have very high production rates that go up early, which oftentimes we can identify clinically without much help, but also these individuals that may look normal originally, but because of very high production rates and perhaps slower elimination, will exceed these thresholds and will need to be treated. And then the individuals who have normal production rates, but are still ultimately going to exceed these thresholds because they have poor elimination, all of these can be effectively treated with a safe heme analog like zinc protoporphyrin. So the biology has all been worked out, and it's been worked out in animals and looks pretty good to me at this time in terms of its safety profile. More work would need to be done by a company with a commercial grade compound. And for that purpose, we think the paradigm that we should be thinking about is one that would be similar to this. Identify and isolate fetal RNA or DNA. We do this now for other purposes in my lab, looking at the signatures for predicting preterm birth and preeclampsia. You create a genetic profile of jaundice risk, looking for polymorphisms in the gene, either in the glucuronidase gene or the heme oxygenase gene. You can confirm that pathology with non-invasive monitoring after birth. You might be able to do this with a simple device that looks a lot like an oximeter, where you could measure carboxyhemoglobin, which is colored, and bilirubin, which is colored, continuously, and get a sense of elimination as well as production in real time. And then target only those individuals for chemoprevention that deserve it. That is, they have high production rates and perhaps have evidence of having less good conjugation. And you could avoid phototherapy altogether. And that would allow you to eliminate the toxic effects of bilirubin and basically to retain everything else that's good about this system, because you could adjust the dose that you're using to only take care of the difference that's represented by the hemolytic condition that's increasing bilirubin production above normal levels, which may be important for just maintaining the antioxidation required after birth when a baby first confronts an environment of light, higher oxygen, and one rich in a variety of other stressors, including iron. If we do that, I think we can have a safer and more gentler approach to hyperbilirubinemia, and can be very rational about how we treat individuals, and not wait for levels to get to a point where they might be dangerous before we intervene, but in fact identify infants prior to that and treat them conservatively and avoid some of the complications, including the potential toxicity of light in some of our smallest babies, where in fact such a therapy, an orally absorbed heme analog that could be effective for a short period of time and then effectively metabolized would be very useful. And one last comment before I stop, I think it's really interesting. We're now collaborating with Impossible Foods, the ones that make Impossible Burger, because they were able to make heme in metric tons for their hamburgers, having genetically modified yeast for that purpose. The same can be done to produce zinc protoporphyrin in metric tons at commercial grade. And you can also fool the yeast. You can take the yeast that are producing heme and simply by giving them zinc instead of iron, they'll produce large amounts of zinc protoporphyrin that can then easily be separated. And it can be done at very efficient levels and approaching 99% even without further genetically modifying the yeast to produce the zinc protoporphyrin. So we think that there's good potential for a therapeutic on the horizon, although we've been saying that for decades. And I'm hoping that we're successful in that regard. And I'll stop at this point in time. Thank you very much.
Well, thank you very much for this excellent presentation, Dave. I mean, you really cover a great deal of concepts and ideas and future. So is anyone willing to interact or raise questions? Don't be shy. So let me start to break the ice. I mean, I think that one of the most exciting idea is actually to try to prevent rather than to treat neonatal hyperbilirubinemia or severe neonatal hyperbilirubinemia. And I like the idea to have a gene screening to see how the baby can be damaged and then to give this baby a more stringent observation. But I think that one of the key issue, in addition to the total bilirubin, is actually the level of the free bilirubin. I think that this may be should be put into the scheme, because if you have, in addition to the total bilirubin, also the idea of how much bilirubin is free, so free to move around the membranes and then get damaged. I think that could be something which has to be additionally inserted into the picture. And I think this is part of the sink, because the free bilirubin is the water into the sink. I mean, getting from above and then not ready to be eliminated. Do you have any comment on that?
I agree with you, Claudio. Obviously, we've done a lot of work on free bilirubin as well. And I think any of us who understand bilirubin biochemistry understand that that's where the action is. And there's not a simple linear relationship between total bilirubin levels and free bilirubin levels, which is the real challenge. I think if we could ever get to the point where we could measure free bilirubin over time, then it would even be a more powerful tool for predicting potential toxicity. Although I think even single measurements may be useful in that regard. So I think that bilirubin still has to be produced, and you can't have toxicity unless you produce it. But I agree that if we could add, in addition, free bilirubin, we might know, again, which infants would be most benefited from controlling the production of the pigment if they can't bind it well. So I think the point you're making is extremely important and relevant to how we manage this problem.
Because it is possible that some babies do have a lower binding affinity, so the same level of bilirubin, you can get damaged. On the contrary, I mean, there are babies with bilirubin of 30 that don't have any damage. So I think this is another, issue, another part of the equation.
Yeah,
Is there any other question? Come on, guys. Oh, Lieber.
Yeah, I have a question. Hey, this is David Steck from the University of Mississippi.
Go ahead.
That was a very nice presentation. I was just a little bit, just want a little bit clarification. A couple of times you mentioned that you're targeting these heme oxidase inhibitors for hepatic inhibition of HO1. And I was wondering, I guess the conventional wisdom is I've always believed or thought was that bilirubin is more generated in the spleen. So why are you using the liver as a surrogate for the spleen, or why aren't you trying to target
Oh,
splenic
yeah.
heme
Sorry,
oxidation?
David. Yeah, sorry. I just showed you that those data in that particular experiment. We actually study it in all tissues, and spleen is in fact probably the most important organ for heme degradation, because that's where circulating red cells are basically taken out of circulation. That was the way the rat model worked. That's the way humans work as well. The thing that was concerning to me, which is why we did the other kinds of studies, is that when you give these heme analogs, you're affecting bilirubin production in many different tissues. And that's why we didn't want to do anything more than what we had to control the production rate as it related to bilirubin circulation, because we didn't want to be adversely affecting what might be essential reactions going on in other tissues related to this enzymatic system. And I showed those in that one slide, which I think is thing. So the point you're making is important. But yes, we measure it, and these heme analogs do inhibit splenic heme oxygenase inducible form as well. And in fact, there's more inducible form in the spleen, probably because of the way it functions in our bodies.
All right, thank you.
Lieber?
Oh, yeah. Can you hear me?
I can, Lieber. Hi.
Oh, good. Hi, David. It was a really excellent presentation. Thank you very much for that. So my question is, what is your explanation for increased mortality in those low birth weight neonates treated with aggressive phototherapy? What's your personal explanation?
Yeah, so that's a scary observation. We're right now in the middle of a study with the NIH, looking at cycled phototherapy as a way of reducing the exposure to phototherapy to see if, in fact, we can reproduce the findings that we saw earlier. But what I'm guessing is that it's photooxidation, maybe involving damage to neurons in the brain directly, because I know that in these tiny babies, we were able to image brain structures using visible light. And so if you use the more intense light that we use in phototherapy, you could be having direct phototoxic effects on neurons in the central nervous system. And that could be what's contributing to the mortality in these kids. But I don't know the answer to your question at this point, and that's just speculation, because you can certainly see phototoxicity in animals from regular phototherapy, and you don't have to have a photoreactive molecule that just exacerbates it. But and that's why the people would worry about it appropriately, because if you gave something like tinmesoporphyrin and shine light on a translucent baby, because you had to in a particular circumstance, even after a period of time, if there's still residual molecule in tissues, you could have a serious problem with these tiny kids.
So
those molecules have never been used in the tiny ones. They've used them only in term and large late preterm kids. They have not used them in these tiny kids.
So you think that it's maybe more important the direct effect of the let's say light exposure than let's say mediation through the photooxidation products, correct?
Yeah, I don't know for sure, because you are going to generate reactive oxygen species, and these might be secondary effects, but it certainly can occur from direct phototoxic effects. And again, I don't know the answer to the question yet. And it'll be really, I think, it'll stimulate the effort to get a alternative to phototherapy for these tiny kids if we, in fact, reproduce what we saw. And that study would be obviously stopped early if we saw increased mortality in the aggressive phototherapy group again, while we did not see such mortality in the group receiving less phototherapy because it's cycled. The interesting thing is we were able to keep the bilirubin levels in a safe range with only 15 minutes of phototherapy out of an hour.
Thank you.
This depends also on the thickness of the skin and everything. So the amount of light entering the tissues is much higher when the wall is less thick. So, I mean, we have to take into consideration all of this. I think this is an excellent. That's why I believe that the lipid combination of zinc protoporphyrin is really genial. I mean, I think it could be really important in.
It's orally absorbable, and a small drop for a breastfeeding baby, or in the formula-fed baby that's starting feeds, is sufficient for controlling the production.
And it's also very affordable in terms of price.
Yep, it is. It would be,
So
like I say, it
that
could be made in metric tons, and I'm not sure Impossible Foods will stay involved in this business, but probably one of the other, like feeding companies or something might pick it up once it's been established.
Yeah, I mean, we should also think in terms of the possible use in the low-income countries.
Yeah, I think again that would be very desirable. I was always nervous about using the photoreactive compounds in the context of G6PD deficiency because they are antioxidant deficient, and that would be the worst of two worlds colliding. So this drug would be much better in that context.
Terry, your turn.
Thank you, Claudio. David, it was a really great, outstanding talk. I loved it. And we don't even study those aspects. We study bilirubin though. So me and Dave Steck have had a collaboration for over a decade, for almost a decade and a half or so. Doing a lot of work on bilirubin metabolism. We showed with the bilirubin nanoparticles that could, reduce body fat percentage. And when we looked at these animals, almost all the bilirubin was accumulating in the fat pads. I mean, it was really obvious. Like when we took the fat pads out, we even took a picture of it just in PBS and showed just to show how yellow it is.
Yeah.
So I was just thinking. I mean, I don't think I've read anything about bilirubin regulation of thickness of the skin. And I was thinking as you was talking, do you think it's possible that bilirubin could be regulating dermal adipocyte, like basically suppressing the dermal adipocyte production?
That's a really interesting idea. Bilirubin, I didn't know that bilirubin did a lot of things, and Claudio has been working on this now more recently. But for example, I've learned that bilirubin and biliverdin are actually important enzymes, molecules that modulate immune function. So I know that these are signaling molecules in addition to the things we worry about. So whether they are in some way communicating with lipid cells, lipocytes, and affecting their behavior, I don't know, but it's a very interesting question.
Thank you.
The other thing that that's interesting about is, of course, when you're dealing with bilirubin, which is in the free form, and it's going to move into tissues, fat being one of them, then the acid base status is important because you'll change the binding behavior of the molecule itself, and it'll move very quickly into lipid structures. So you could change the amount of bilirubin in lipid quickly by changing the pH.
Any other question?
Thank you.
Well, if not, thank you again, Dave, for this excellent presentation. And let me take this opportunity to wish you and your family Merry Christmas and a new year full of joy, peace, and health.
Same to you, Claudio. Thank you very much, and to all my colleagues. Good to see some of you, and hopefully we'll see each other in person soon.
Absolutely, soon, hopefully. Ciao, ciao.
Okay.
You take
Bye-bye.
care. Ciao.